Hey, I have a problem. And probably if you're watching this video, you also have a problem, even if you don't know it. And it's a problem called TRPO. And no, in fact, it's not a venereal disease. It's an algorithm called Trust Region Policy Optimization. I've tried learning deep reinforcement learning, and I followed the book by Sutton and Bartle. And after finishing chapter on policy, basically optimization, policy gradient, it just felt like I struck a wall because there wasn't enough information, not enough exercises I can do, and all the papers which describe the methods were very complicated. And so in this video, or at least I plan to do 2 or 3 videos that would lead up and explain the TRPO algorithm. And so I just hope that first my observation is that there's not enough information on this topic. There's a lot of information about the theory, but I think there are no proper, easy to understand implementations. They are on really high level. I mean, in terms of abstraction, there's one on GitHub. I can get it in the first result of Google search, or OpenAI's implementation. Well, also their baseline and different reinforcement learning packages that implement it, but still they're implemented it on very high level of abstraction, and it's really hard to understand. So okay, I guess this is my option, my chance to cover these holes, at least on this kind of platform in video form. So yeah, trust region policy optimization. If you have a glance, if you take a look at this, basically description, algorithm description, hopefully you've covered basically simple or called vanilla policy gradient methods, because there's plenty of information regarding the topic. So probably you're familiar with most first steps, like how to collect data from the environment. You're familiar with how to form rewards, possibly advantages, value function estimation and such. You've also encountered how to calculate a gradient of a policy. But from step 8, you can read the step 8. Use the conjugate gradient algorithm to compute some stuff. Like what is conjugate gradient, right? And you can keep reading, where h hat k is Hessian of sample average k of divergence. And you're like, what? What are they talking about? At least it was the situation for me. And then update policy by backtracking line search with, etc., etc. It's just crazy. If you haven't encountered such algorithms, you probably are really desperate, depressed, I don't know. So this will be my chance to give my thoughts and do a small crash course on all of these topics. But generally, the main problem, I think, with TRPO is that you don't exactly derive at the same as all the previous iteration, like vanilla policy gradient, even the natural policy gradient. So the theory is really different. Although many papers write, at least different resources, that TRPO can be viewed as an extension of a natural policy gradient. And in fact, they're really similar. They basically share most basic concepts. But the theory actually is kind of different in TRPO. So I kind of open the paper and I read what they're trying to say. I see all most familiar things, like discount the rewards. Well, some new kind of definitions, but the idea is easy to understand. Action function, value functions, advantage, everything is already familiar, but then they follow up with some kind of expression which I'm unfamiliar with. And then using this expression, they derive basically the algorithm. And I can't follow it as easily, at least in this format. So I kind of started searching. I couldn't find anything, and I cling to the idea that natural policy gradient, if it's kind of similar, that maybe I should at first master that one, and probably I could extend it. In a sense, it's a good idea, but now, in retrospect, I would say like the theory part is too different, absolutely different. But what I propose is that we get a good grasp of natural policy gradient, and then I will try to extend it to trust region policy optimization. So this is our goal, basically. We will repeat a vanilla policy gradient briefly. Maybe I will give some interpretation, some interesting aspects, ideas. And vanilla policy gradient is easy. Then we will go to natural policy gradient, and there we will derive basically most of the TRPO stuff, almost all. And probably in the next video we will talk about TRPO exactly. So this is our goal today: VPG and NPG. And so let's start with vanilla policy gradient. There's a lot of information. You can check the resources, especially Spinning Up, OpenAI resource. But the general idea, I hope you've done previously reinforcement learning and you're familiar with these ideas already, but that we launch an agent into our environment. He collects rewards. We remember which actions he took based on his observation states. And then we try to improve his brain, his policy, to such that in the next iterations, in the next experiments, he will gather the better total reward, so cumulative reward. It can be discounted, but I hope you're familiar with it. These are basic definitions, very, 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 very easy. So let's look at the basically policy performance. So we want some kind of measure to tell us whether the agent is smart or dumb, right? And the natural idea to think along which lines is to think that we will release this agent in the environment. He will go through through some kind of trajectory of actions, states and actions, and he'll collect some total reward, and we will just repeat these experiments over all the possible trajectories, basically, and gather some kind of statistics, whether his actions result in good rewards overall, right? And that's what this expression means. But here we actually assume that we know probability that some kind of trajectory will occur, although we can estimate it because we conduct many experiments. And this is the frequency of basically trajectory, in a sense, right? And we write it like an expectation that trajectory was taken using some kind of policy, and the rewards, basically, we average all the rewards. Probably because this is deep learning, or in general, we want to parameterize our policy, unlike if we're using tabular approaches. It's kind of parameterization also, but here we want a policy that will generalize. And we will, of course, use neural networks for it. So we are parameterizing our policy with some kind of parameter vector theta. We give it state. We can ask for a given state what is the probability of take this action. It will return us the probability. We can ask to give us a distribution over actions from a given state, probability distributions, right? And so idea is to basically maximize the performance of our policy, and that means we can use a gradient ascent in this case and move along iteratively, basically improve this policy if we move along the gradient of this performance metric. That's basically gradient ascent step. Hopefully you're familiar with it. Exactly, we don't exactly know what is the gradient of this expression, because we actually have to measure it. We have to estimate it. Well, so the idea is that we have our definitions. We take the gradient. Gradient, it only concerns with the probability of trajectory, but we don't actually know the probabilities of not the probabilities, but the derivatives, basically, with respect to parameters of. It's kind of difficult to tell, but what we can tell, at least what we can use to help us, is use this expression. Basically, when we take gradient of a log of a function, it is a 1 divided by a function times the derivative of a function, right? And it's just we swap terms here and get this expression. Now we see we get a log of a probability that trajectory will occur, kind of likelihood. And we have defined this previously. We didn't talk about it, but probability of a trajectory is kind of a product of different probabilities. Some of them are environment controlled, some of them are agent controlled. So basically, if our chain of trajectories from state 0, we take action 0, and then it brings us to action S1, and so on and so forth. You can write the probability of a trajectory is just the probability that you will start at state S0. It's taken from an environment, from its distribution of initial states, and our agent uses policy to decide based on this initial state which action to take, and then the environment responds and say, okay, you've taken this action, And we have observed that you've moved, that environment moved you to next state, right? But it's also a stochastic process. In fact, we are examining so-called Markov decision processes, which are stochastic in general case. And basically what we see is that there are multiple probabilities, chain of probabilities that correspond to our single trajectory. And the total probability that this trajectory will occur is just a sum of, not a sum, the product of these terms. But in our definition, we take a natural log of this. And if you know that natural log of product is a sum of logs of terms, and then we take a gradient of each term in a sum, right? This is the idea. And of course, only policy is parameterized with data, and that means initial distribution drops out. Whatever environment decides stochasticity in this response, it will all drop out, and you will be left with a just with this expression, which is the right part of this expression. We just plug it in and get an expression that our gradient, so direction in which we would like to basically move our parameters, is defined as such. Now there is kind of interpretation. I don't know, should I tell you now or should I tell you later? But yeah, because if it's a sum, you might think that in a sense they are kind of independent, and problem here is that we use rewards for the whole trajectory. It will not be the case later. You can like imagine that each step, for each action you get some kind of reward, all right? And then what this gradient would mean is that if you get higher reward, let me see. Here's the good example. So our total gradient is a function. It consists of sums of different gradients, and these gradients, they are nudged into negative or positive direction depending on either you get positive or negative reward, and also the magnitude of this reward. So kind of this is the idea. It doesn't work with a cumulative reward because the whole set of actions gets nudged either in good direction or bad direction, right? But we will fix it later. And I guess this is the main idea, that we can calculate the update step using gradient ascent for our policy, just using this expression, as long as we have a differentiable policy in case of neural network and using auto-differentiation capabilities or library, we actually can do it. Maybe in practice for this vanilla policy gradient, you don't actually implement manual, basically, iterations. You can just extract basically the objective function. So in this case, I would say I can bring the nabla, del, the gradient outside of the sum, and I'll just consider this J prime is some kind of objective function, and we want to basically minimize or maximize it. Of course, typically neural networks minimize stuff, so you just plop minus sign in front. One thing also I should mention, that our estimation over trajectories, as I alluded in the beginning, so it's basically, originally it was, we try out, we know probabilities for all the trajectories. So instead we estimate it by repeating different trajectories. So this is objective function. We will basically, I have optimized it using Adam optimizer. There was a case of pendulum, not pendulum, but pole card pole. It kind of learned something in 50 steps. It's kind of slow, I'll be honest. Sometimes it takes minutes, which is a lot for such a simple problem. And the next idea is so-called rewards to go. So as I said, that if there was such an option that for each step you get a separate reward, it will nudge basically our policy. It will either improve or decrease performance of our policy of individual weights depending on the gradient of policy. So this idea kind of is to drop the total reward, the cumulative reward, and say that actually maybe some action at time t is affected only by future rewards, t up to t terminal. And this is the idea behind the rewards to go. Basically, instead of multiplying by 1 total reward for this trajectory, you just keep basically a reversed cumulative sum and reversed again if you're interested in implementation. I've had it somewhere here. So yeah, basically you gather all the rewards in the trajectory, and then basically you flip, do come sum from back to start, or in flip case from start to back, and you flip it again. Just not that important, but very easy. Sometimes I see people implemented it to way more difficult. In this case, it's very let's say variance of this experiment of this learning is high. So the fact that it learns way better and it learns faster, it's not representative of this image. It depends on the case, basically, random initialization. Okay, whatever. The next idea is to say we also can implement a baseline. And this is kind of important idea. The problem, I would say, again, if we think about our gradients, how to improve our algorithm. So imagine a case. Some people explain it differently. You have some kind of state 1, it has some kind of 3 actions, whatever, and each action has some kind of rewards, whatever they are, right? And then the agent kind of explores this space of trajectories. Depending on his current understanding of a system, he selects one action, it brings to some state 2, and you imagine this state, it has rewards 100, like plus 100 100 rewards units higher than the previous state. And then there's a logic, basically. There's some kind of probabilities associated with state 1, the actions, whatever he took, and some kind of probabilities with state 2, but basically all the time agent took actions and got rewards 2, 3, whatever. And at some point he took action from this state where actually each state gives very high rewards. So if you remember, we had a sum, basically, right? And basically these gradients, they were nudging certain entries of our parameters based on the magnitude of rewards. Not the magnitude, but sign is also important. So here you can imagine that once he explored this state, actually first time he's here, and he took random action, whatever action he takes, it gives him like 100 or more rewards from here. And then when we're actually calculating the gradients, he realizes that this action that he selected, like action 1, it yielded him such high rewards that basically when he calculates the gradient, he will push this gradient so far, basically he will think that this action is so important that all the other actions will basically diminish probabilities. Agent hasn't actually explored it. That's the problem, right? But then if you think about it, if the rewards were actually something like current reward for action I minus the average, it would be the same 1, 2, 1, like he wouldn't have even realized that there's a difference. And this is kind of an idea that we don't let the high rewards, if they are not that high in relative terms, to influence the gradient, because reinforcement learning is very fragile if you take basically bad steps, if you basically break your policy. If you break your policy, it may break all the whole learning process. This will be also, of course, used in exactly, okay, maybe not exactly these implementations, but rewards to go will be calculated. Base function, when we're talking about this, okay, average, right? In fact, we can say that we can replace it with value function, which is the same but kind of different. Value function, if you remember, it was an expected future rewards. So basically, how valuable is this state, given that I will keep, I visit the state and I will keep basically following the same policy, and that was the idea. And of course, we can approximate it using neural network. Here's a small example. I have just multi-layer perceptron with well, yeah, it's just how it's called, not guided learning, but oh god, I forgot the name. Okay, just the basic optimization where you know the results and you know the output of your neural network. So, which is not completely true for reinforcement learning. There's a subtle and important difference there. So yeah, basically, while your basic agent travels, explores the state, you can basically after each trajectory do a little fit on a value function. And the actual implementation, at least in this case of spinning up, they decided that they will not use every single trajectory, and then they will not optimize after each single trajectory because various reasons. It's not representative. Each individual trajectory is not representative of actual dynamics. It's not enough information. So they just concatenate together a bunch of episodes. In our case, it was like 5,000 steps. Given that 3,000 steps, 300 steps for a card pool is not maximum, but at least a popular cutoff. So a lot of trajectories, and they do all this process using the batches, including policy learning. Well, and kind of performance, it didn't improve drastically, but I can rerun it. Probably it will show you something different. But still, it's important that it works, and then it maybe start to shine on the larger problems. So this is the idea of standard policy gradient called vanilla policy gradient, where we are defining this policy performance metric, and then learn how to calculate the gradient. And you will see this expression later. Now we will transition to natural policy gradient. It's they are using a bit different idea. So let's just think about it. As I mentioned, like the learning data is basically very noisy, or you have to gather a lot of trajectories to get at least good mean, but still it's a stochastic process, all right? And some trajectories, they will push the gradients very hard, and if they push the trajectories, the parameters so far that policy degrades, we have a problem, because if policy degrades, agent will start basically exploring states that don't give good rewards, and you have to keep learning from the current data on this policy, but the policy is bad and the data is bad, and basically you're stuck in this limbo. So it's kind of hard to break out. I'm not even sure. Maybe this is why in the end, or was it sort of algorithm reached something? Maybe it started to overestimate. Again, it's optimized. I control the step, right? I guess. And it started to degrade the performance. Maybe that's why, I don't know. So yeah, you can actually break your learning by performing bad parameter updates. And so the idea is that as a safeguard, we can say, okay, let's limit how much the policy can change. But the problem here is that how do you define how much? Because parameters, metrics, these metrics and then metrics, weights and biases in a neural network, these are some kind of numbers, and you can maybe take some kind of norm, right? But it will not be representative. We need a measure, not in a geometric sense, but in sense of distances in a policy space. So how one policy is different from another policy. And then if we pick this metric, then maybe we can check it and say, oh, this update is too big for to be basically safe. And then we reduce the step or derive the step as basically as a function of this metric, which we will do. Okay, we start with a place that has this vanilla policy gradient left off. We have an update rule with some kind of step learning rate, step size, whatever you call it. And the definition of gradient, I will call it G, just to be shorter. Well, the meat of this basically algorithm is to use a KL divergence. So I hope you're familiar, at least you've heard what KL divergence is, but it's basically a measure of how different are two distributions. In fact, even if these distributions are not of same class, right? You can compare a normal distribution with God knows what. I don't know the names actually. Okay, log normal, I don't know. Pose+solve. Wait, it's not continuous. Okay, never mind. So the idea that there is such a metric, one of many, but this is one of the most popular. It in a sense satisfies the distances in a kind of not qualitative way, in a sense that if we are trying to measure the distance between the same policy, it will just be 0 because of this. It's not symmetric, unfortunately, but usually it's enough. And we want to use this measure again to say, to determine the update step size, learning rate. Okay. And actually, it's not easy to calculate this KL divergence for any case, but in this particular case, we can show that for NPG, that we can express it in terms of things that we actually use for our calculations. In fact, you see this gradient of log of our policy, and you see we will already use it for our gradient expression. And I can just make a kind of fast crash course just to how to derive this stuff. So in a sense, the proposition is that KL divergence can be expressed in terms of different quantity that's easier to calculate, and this quantity is Fisher information. In multidimensional case, it's called Fisher information matrix. And the expression for one variable is such, its expectation over square of log probabilities, log likelihoods, you know. It can be whatever. You can express it in terms of not square of first derivatives, but in terms of second derivatives. Actually, we will use this for TRPO. what we can say, what our goal will be, is to compare a policy and a policy that's a little bit perturbed. So we've changed parameters a bit, and we want to say, okay, how did this perturbation impact? If KL divergence between this normal and perturbed policy is big, then probably we should reduce the learning rate. In fact, our learning rate will be a function of this, so basically don't sweat about increasing or decreasing. You can just rewrite this expression as it's an expectation, so it's kind of integral over p of x. Or you can rewrite it in this way, and what we propose is to expand this perturbed policy in Taylor series up to and including second term, and some stuff will cancel out. If we take an expectation is linear, we can split it into sum of expectations. So what I show you here, that the second term derivative of log, we know how to rewrite it in a different form. So basically this term becomes 0 because we can pull the derivative out of this integral, and we just integrate the probability which is 1, and derivative of 1 is 0, and so on. Right, so we're left out with a term which is minus second derivatives times this nudge squared. Now we actually cannot repeat it. We cannot do the same here because we would have to take a derivative of this expression, and clearly there nothing will cancel as beautifully as here. And it just says us that KL divergence of policy and a perturbed policy is at least approximately up to second order is proportional to this Fisher information matrix. So maybe KL divergence is hard to calculate, but clearly, well, let's look at the original definition. We just can reuse our log gradients of log probability, just square them and such. So it's cool. Well, except our problem has multiple parameters, not multiple, effectively we'll have hundreds of control parameters in our neural networks. So we have to consider the basically multi-variable case is that. And if you take a look at the definition in Wikipedia, you will say it is not the square of same probabilities, simply if you have n parameters, it will be n by n matrix, and the entries aj are just such. So basically, if it's 1D, if n equals 1, it reduces the previous case. And I try to basically prove this expression again. Yeah, I just say, okay, our theta is not a scalar, it's a vector, and we'll just expand it in Taylor series for multivariable case. So constant term, linear term, and the quadratic term, in this case H is a Hessian matrix which contains mixed derivatives. This kind of expression is important, but you can rewrite Hessian as decompose it into Jacobian of a gradient if you're not familiar what a Jacobian is. You're familiar already with the gradient. So the Jacobian is just an operator, it's a row vector. And you can imagine if we plug in the like here's the example for Hessian. If we plug this, apply this row operator onto gradient, we basically retrieve the Hessian matrix of mixed derivatives. Okay, we were in Fisher information. So what I try to do is basically we can repeat basically the same stuff will cancel out. I guess the linear term, each term is a derivative with respect to something. It will cancel out. It will be a zero vector here. And we will be left with this Hessian of log, and I rewrite it as this kind of decomposition, alternative definition, right? And then I'll try to calculate what it is. Basically, we know that the ith entry of a gradient of our log, which we rewrote in this format, and then it's an entry of a column, and then we take jth entry, basically jth derivative as in Jacobian. It's a product rule in a sense, right? So what we observe, we can split the bottom half into two terms, and these are the log, and these are the derivative for logs. This partial derivative ij, it's just a mixed derivative. It's an entry of a Hessian matrix. And if you write this whole expression in matrix or vector notation, we all know that here's this kind of ith entry of v times jth an entry of v, some kind of vector v. And basically what it is, it's an outer product. I hope you're familiar. And okay, so our h log of this stuff is here. We have calculate, we have to take an expectation. Actually, this h is, again, it's an operator of partial derivatives, but in a sense, again, if you remember, we just took it out of the integral, and we were left with just integral of probabilities over all the options, basically, which is 1, right? And we have derivative operator on 1, it's a zero matrix. And that's what we're left. Up to second order, we can approximate this KL divergence as this entry. Again, if we remember, we have some kind of ith j entries of gradient. It's exactly this expression. So our Fisher information for 2 dimensions also works here. Maybe it's worth to mention that the way I did here, that I basically I have expanded inside of KL divergence. I guess it works, right? But usually people start more abstractly. They say that we will expand whole KL divergence. It will be KL. I guess it's not here. It's written somewhere else. But basically, it will be KL divergence of the constant term of p with p, which is 0 because it's the same plus linear term. But we actually, by the same logic, we have dropped the linear term there, and then it will have a second derivative of KL divergence, which is this Hessian matrix. So kind of this Hessian, it is the same as in this approximation as Fisher matrix. It is the same as basically second derivative of KL divergence, mixed derivatives. We will see this expression later. And that's the takeaway exactly for natural policy gradient. that we can approximate up to and including second order of KL divergence as this kind of nudge transpose times Fisher information matrix times this, again, displacement. What is the meaning of Fisher information matrix? Again, we know what KL divergence means. It means if something is different from something else in terms of, if we compare probabilities, then the KL divergence is large. So in a sense, we can think that Fisher information matrix shows the measure of how sensitive the distribution is to small changes in parameter. So Fisher information matrix shows the sensitivity. And it's kind of important idea. Well, there's like a more formal definition. It's kind of curvature or some kind of Riemann space manifold. I don't know, Riemann curvature, whatever. It's something crazy, but definitely it's related. Second derivatives are usually related to curvature, but in this case, it's not related in geometric terms. It more explains this curvature in space of policies. So if you're not familiar, it's kind of optional, but I will tell you real fast. If you learned optimization, specifically Newton's methods of second order, you will know that using this approach, we locally approximate the function that we're optimizing as some kind of paraboloid. And then for this parabola or paraboloid in many dimensions, we know how to analytically calculate where its minima is. This is basically the idea. We expand f of x around some x0 where we start, and this is x minus x0, x0, it's a displacement. And then we are searching for special x where the gradient is 0, basically the minima. And we calculate the gradient, we solve for this special point, and we get this expression, which is a surprise. It's an kind of parameter update rule, which is basically the same as steepest descent when we use gradient, but in fact here gradient is transformed, so its direction is gradient is redirected in some way that will help to basically optimize faster. In fact, you can imagine if this f of x is actually a quadratic form, and we approximate quadratic form with a quadratic form, that means that actually this solution gives an exact solution in one iteration. But when this function is not quadratic, so you can imagine that some kind of here's some kind of function. At least it's an objective function with respect to parameter, and then we want to say minimize the subjective function. We usually in the first order we are moving down slope against the gradient, but in this case method says we're constructing, basically we're here, we're constructing a paraboloid, we're searching it's kind of bad case. Let's say we're constructed a paraboloid like this. We know the solution of this minima. We project it here, and basically we repeat the calculation and basically create these approximations and basically select their minima and so on and so forth. Of course, if we're examining again, this idea, the objective function is actually a probability itself. It will actually find a solution in first try. And that's the idea. Actually, you see, there's no a learning rate, basically no step size. And the curvature, it tells you something about how to do steps. You can imagine if you have high curvature, how to tell it? Basically, the relation is inverse. When you invert the curvature, you say that when the curvature is high, big, the step size must be small, right? And it is exactly what we expect. Unlike gradient, high gradients say move faster, move longer in that sense, right? But this is easier to understand. If we have a low curvature, then it means the step size will be larger. So it's kind of, it selects the proper steps on its own, just using information about the curvature. So you can say it's very robust. Okay, then it was kind of a tangent. We've discovered how to actually implement the KL divergence. Here's the implementation in box. Now the question is, how do we pose a problem? How do we actually, basically, what is the algorithm for optimization? What is the main rule? And the main rule is such that we want to nudge this policy, its parameters in proper direction. In this direction should maximize the performance metric, but this increase in performance should not be very big. We should limit it by our KL divergence. And by the way, I think Schulman's video or some kind of Google bootcamp or whatever, also there was an example, someone else, I don't remember where. So the idea is why it's dangerous to do large steps in policy parameter space. You can draw it. Okay, there was such a graph over, again, the same thing we've drawn before, over parameters, and here's the performance, and you're at some, I should draw it with my pen, you're at some state, at some iteration of your parameters, and you say, okay, follow the gradient or whatever. If you actually, your algorithm is for some reason overly confident about its step size, it may jump here, it will end up here. It means it will update your policy, then it will measure basically your experiments, your trajectories, it will return the data, and you start examining the performance, and performance is very poor. And even if you start changing a bit your parameters, overall your policy is broken. And as you see, there's, in this kind of simple, it's not realistic. Maybe in some sense it's realistic, I will tell why. In this region of parameters, there's no discernible gradient. Algorithm will be stuck. It is the case if you say, if your algorithm, if your environment gives only positive rewards and these rewards are very sparse. In fact, probably probably you should implement some kind of penalties, and then if your policy is very bad and it start to reach bad states, it probably should start receiving some kind of penalties for being there, and then okay, it will be negative policy, but it will not should return. Maybe that's a small comment. So yeah, we want to find kind of maximal possible change in policy that will increase our performance, but we don't want to make it, we don't be overconfident with this step size. But this is kind of constraint optimization. It means there's some kind of parameter space, and then we set a boundary which we cannot cross. Our algorithm just cannot pass it. It's not an easy it's not an easy algorithm. Constraint algorithms are way harder than unconstrained ones. And so the idea is that let's make it into unconstrained algorithm. So we're observing that if our KL divergence is larger than our some kind of threshold, then it means it should be penalized. So we introduce a penalty function, or I just basically subtract from the right part, whatever, and the same logic applies. If this stuff is larger than 0, then penalty is enabled. In fact, that KL divergence is non-negative. This term will be always negative until the policy is violated, and then it will ramp up and become positive. So it's violated. When it's violating, it's positive. That means we want to actually, if we're maximizing our performance, we want to add it with negative, some kind of coefficient. And so this is unconstrained optimization. Well, the idea is that we approximate this perturbed policy using first order. So it's just at start where old policy was, and plus the gradient. And then we have to do something with KL divergence. Of course, we approximated it using second order, and we just replace it. And that's what we get. Our task is gradient of performance times del and the KL divergence. And the remaining factors, as you will see, if we're optimizing something, they are just constant with respect to our task. And so this is our objective function. And then we just ask, okay, which displacement, this nudge in parameter space, will basically where it's minima. And so we just take the derivative with respect to this parameter. We are left with this expression, and it will be 0 in the minima with some special minimizer delta. We can solve for it. And if we remember, our gradient ascent was this, some kind of learning step rate times step. We just replace it. What I propose, this 2 divided by lambda, is to absorb it into this step size. And it's kind of first milestone, because we have an update rule that knows the direction at which to move. Using our, well, actually, if you observe it, the only time that this epsilon appeared, we just dropped it because we were differentiating, it would be dropped anyway in this case. It could be like 10 million, you know, it could be 0, I don't know. It wouldn't play a role for this expression. So what we're asking, okay, can we some kind of implement this learning rate in such a way that it will involve this threshold value? And we just calculate the KL divergence of this perturbed policy by exactly our step size times learning rate. And what we discover is this expression, then it should be smaller than epsilon. Now, you know, you can change the order of second derivatives. That means Hessian is the symmetric matrix. Also in Fisher information, it's a rank 1, basically outer product, you can do it. But the general idea, you can just cross terms here because they are identity, and you are left with this expression that our step size squared should be less or equal than this expression. But we kind of want to increase the step size. So instead of less than or equal, we should take the biggest possible, which is equal. And this is the expression. If we combine it, we get the update rule for our natural policy gradient. And it's pretty much it. Because, okay, there are problems. We can calculate Fisher information matrix. If you remember, it was an outer product constructed from these gradients of log of policy. Then we have our gradient. Surprise, it's constructed from the same stuff. One problem maybe is we have to invert Fisher information. So each iteration we have to do it. It's expensive. It takes a lot of memory. That's a common thing to say, is that if your neural network is large, this matrix may be n by n, and this n can be huge. So this will be solved in TRPO. Maybe this Fisher matrix, it contains, basically it's very also stochastic because of we are sampling it. Problem may be that it's singular, basically it's not invertible. There are also assumptions that Fisher information matrix should be positive definite, and such. It is not the case. Maybe if you want to implement this case, what the hell? There are a few tricks. Actually, there are resources where I've looked at, and they didn't do the same actually. So the most problematic part, I think, here is one, that you're updating your parameters manually. And when you ask your network its parameters, it will say, okay, this first layer will have matrix this, then it has a biases vector, and then and so on, and so on and so forth. You actually have to concatenate them and flatten them. And then you have to basically, during update, because you're doing this manually, you basically have to assign them manually, and maybe you will have to use already. It's not simple because no one does it. but it's okay, you have to do it manually. And then there's this inversion question. There was a resource where a person had a problem with inversion because of rounding and such, or there's a difficult topic. It's about eigenvalues and lack of information and boosting some directions over another. But this person had some kind of problems with inversion. I actually asked, it didn't work for me actually, this step. I've tried different steps. I've tried saying it's a Hermitian matrix using pseudo inverse, but the solution was actually ChatGPT just provided me that you make it positive semi-definite by boosting its diagonal. I will not go into that, but if you encounter this issue, it's a common technique. It's called Tikhonov or Rich regularization. Yeah, that was problematic. And implementation, maybe everything is somewhat basic. Question is, how do you take gradients? In PyTorch, you can take gradients only with respect to one parameter. Not one parameter, but of a scalar function. And then you have your trajectory of log probabilities. And then you actually have to loop through them. It's kind of bothersome. And then you have to flatten them up. Outer product is very easy, but you cannot broadcast it, you cannot batch it in PyTorch, but you can do it using like expand dimensions and such. This is all the stuff we've talked about. And yeah, it works. And if it works and it actually performs, it's a miracle. Because most of the time you're missing somewhere a sign, a single sign, and then basically you have no progress at all. So it's kind of a miracle. This will end this video. Let's briefly cover in these notes what we've talked about. We've covered the basic concepts of vanilla policy gradient. I've tried to convey you the idea that how this basically what happens with neural network weights, how it depends on rewards, and that the rewards are nudged proportionally to weights are nudged proportionally to basically rewards. Well, along a gradient, in that sense, this is important idea, and this idea means that if we have stochastic rewards, which at some point may explode for some reason, or something unnatural, your policy may break because it changed your weights too much. And that's what natural policy gradients try to fix by introducing a measure, basically distance measure in parameter space, and then we've implemented unconstrained optimization where we implemented this loss inside, and we found the basic direction at which we have to nudge our parameters, and then we've implemented actually a step size that is controlled by actual threshold, KL divergence threshold. This video was way too long, but again, there's a lot of information. Even the beginning was kind of long, And usually I would expect people to know it, but then again, these ideas about breaking your learning are super important. So in the next video, actually, we will, as I said, go over the theory of how TRPO is derived. It's basically derived using same loss, same performance measure, but then it's derived further using this expression, which was not apparent for me what it does and why it's used, and it's not intuitive. And then when you open the paper, you reach there and they don't explain anything. Okay, they referenced some paper and I didn't read it, but still, that's why I turned into natural policy gradient, which is supposed to be similar. In final steps, it's similar, right? So we will show why this expression, maybe how to using this expression derive a function that improves the policy using our old data, and what constraints, again, KL divergence will be a factor there in the same way but kind of different, right? And then we pretty much repeat everything we did before with few minor exceptions, with that we don't use Fisher metrics, but we calculate directly KL divergence, and it's Hessian. We don't calculate Hessian, we do it as a Jacobian of a gradient, which is much easier and faster and doesn't require much memory. But that implies that we have to calculate KL divergence, and that means that we have to know how to calculate it, and basically that we have to, at best, we have to have a parameterized policy. In this case, in many applications, they say, okay, discrete cases are easy, really, I don't even want to talk about them. But in the case of continuous actions, then they propose to use normal multivariate diagonal distribution. And that's where all the interesting stuff begins, at least for 15 minutes. 15. And that's where I think my input is most valuable, because you have to fight through the maths, at least how I interpret it. And we magically arrive to all the steps. In fact, I will talk even about the conjugate gradient, a small crash course. So stay tuned. And I guess third video, if I will get there, I will try to do an implementation, because current implementations, as I said, are crazy difficult. They're way too abstract. Like OpenAI's version, it's written in using PyTorch, not PyTorch, but TensorFlow, and they use the placeholder, this abstraction, and it just breaks my head, because they don't call for a function in a sequence. They just call, okay, this variable was, give me this variable, and it searches all the paths up to this variable, whatever it needed. It's crazy. So yeah, I hope in third version I will actually implement it using PyTorch in more readable format. There is one implementation also available, which is much easier to read, much shorter, but it's not easy to understand, because you take gradients there, in which you have to free the computational graph or let calculate gradients. It's a mess. I will have to fight through it also. And yeah, I will see you in the next video. Thank you.